Hello.
Yes,
Okay, so let's get started. I hope
okay, sir.
whoever wants to come has already come. Okay, so let's present. So we were. Okay, so let's see where we were. We were looking at. Okay, so hope my screen is moving, right?
Yes, sir.
Good. So we were looking at atoms and their. So essentially, what we said is we did crystal structures, unit cells, lattice directions, and planes, Miller indices. And we briefly discussed crystalline nanomorphs, which we'll talk about a little later. What we left out was atoms and their binding, so we will continue that now. Okay, so let's go to the point where we were. So this is where we left out, right? The BCC unit cell
Yes, sir.
and the packing density, and then we said that we will leave the FCC out as an exercise, which I will post today after the finishing of this chapter. And we realized that each of them have different packing densities, and then we said something about, so the moral of the story, that the reason that we talked about the packing densities is, can you figure out now how the lattice constant, that is the A, what does it depend on essentially? What is the physical understanding of what the lattice constant is related to? From this diagram, can you figure out what is the lattice constant related to?
So the number of unit cells.
No, the lattice constant, the distance, the A. What is it physically related to? My question was, I can tell you in lattice constant of silicon atom is so and so, but what does it actually depend on physically? From this diagram, what do you think it is?
Radius of the atom.
Yes. See, if it is a BCC structure, then this is how lattice constant will depend. If, because the radius of the atom, that is the bond length, is something that is a physical parameter, right? That is something dependent on the nature. Crystals or silicon, for example, has a particular radius of the atom, or basically the bond length itself. If there are two silicon atoms which are bonded, the distance between them is something that can be measured, and that is given. Okay. So based on that, you can calculate or you can estimate what lattice constant is going to be. Good. So based on that discussion, we have now a whole series of lattice constants. Now, you have, what are these? Can you tell me? What are these compounds?
The semiconductors.
Yes, they're all semiconductors, which is very interesting, right? Because usually when you talk about semiconductors, we talk about silicon and germanium, and that's about it. But as you can see, there's a whole huge list of semiconductors, which are, all of them are important. So if I were to ask you, which is the most important semiconductor, what should be the answer be? If I were to ask you which is the most important semiconductor, what should be the answer? Hmm?
Silicon.
Why? See, the answer should be essentially that there is no the most important semiconductor. All semiconductors have their own unique uses. Okay. For example, silicon is used in a certain way, and all of these materials, for example, if I put a material at random, say cadmium sulfide, if this does a task in technology and in the nature and in our daily lives, which other semiconductors cannot do. Okay. So all of these semiconductors are important and they all have very, very strong technological benefits. So we'll come to this point a little bit later. But what I'm trying to tell you is there is a whole series of semiconductors, and these are their lattice constants given. You do not have to memorize them. What is important is can you see they are all close to each other? They have a certain range. Can you see what the range is? They are all around 5 angstroms, between 5 and 6 angstroms. Yes?
Yes, sir.
Okay. So that is because, of course, the atomic diameters are not hugely different. Okay. So that is the reason the lattice constant have a particular value. So based on this, that idea that the crystals are related to bond length, that is the distance between two atoms when they are stable. I think somebody's trying to call me. Let me go back and admit this person. So try to come on time, otherwise the class gets disrupted. Okay, so here we go. So with the idea that crystals are directly related to bond lengths, we start talking about bond structures in a little while. Before that, let's stick to this particular difference: polycrystalline materials. So, what are polycrystalline materials? As I said in yesterday's class, almost everything is polycrystalline. It is very difficult to find single crystal things, but you know, diamond, for example, is a single crystal material found in nature. Gemstones are, but most materials are polycrystalline. So, what are polycrystalline? Can you see this picture? This one.
Yes.
So each of them is essentially a crystallite. So these are individual grains which are crystals. Can you see the atoms? Diagrammatically shown this way. And in this
Yes, sir.
other grain, the crystals are oriented in another way. And in third grain, the crystals are oriented there. So essentially, each of these individual grains are crystals, but they are very small and they are misoriented with respect to each other. And these are something called grain boundaries. The grain boundaries are present between grains. So single crystal is when the grain is larger than the material. So it's a single crystal. It's a whole material is a single grain. But most materials are not single crystals. They are something called polycrystalline material. Now, can you tell me what is the advantage of a polycrystalline material over a single crystal material? What do you think is the advantage? Guess. Make a guess. Anybody? Make a guess. If I give you a semiconductor that is polycrystalline and I try to sell it, this is the biggest advantage of this. What would be my biggest selling point? Anybody? Try to make a guess.
Sir, is it something related to doping?
No, it is something related to cost. It is much cheaper than a single crystal. Okay. So polycrystalline materials are by definition a lot cheaper. Okay. Now, if I were to make a device which is large, it requires a whole lot of material, and I want to make it economically viable, then I have to go with cheaper materials. Now, can you tell me of a semiconductor device which gets more useful as it gets larger? Usually, all semiconductor devices are more useful as they get smaller, right? But there is one device that is more useful as it gets larger. What is the one device? For example, transistor. Transistor is much faster as it gets smaller. Yes. So what is the one
Yes.
device that is more useful as it gets larger? Can you think?
Carbon.
No, device. Device. I said semiconductor device like a diode, transistor, LED, whatever. Which device? No. LED is small is good, right? The solar cell. The solar cell, as you realize, the larger it gets, the better, right? It can collect more light from the sun.
Yes, sir.
Yes. So basically, it has to consume more material to make solar cell because the larger it is, the better. Ideally, I would like to cover my entire roof with a solar cell if I can. Yes. So the cheaper, more useful solar cells are made out of polycrystalline silicon because they have to compete. What does a solar cell compete with in terms of cost? It competes with conventional generation of electricity, right? The thermal power plant and the
Yes, sir.
okay. So if you can produce electricity cheap using the solar cell, only then people will get electricity from the solar cell. So cost is a very important point. As I do not know if you're aware that the price of oil, okay, that controls essentially very clearly it controls if electricity is produced by solar power or by conventional sources. If oil gets more expensive, then people will go for solar cells because part of oil is natural gas and what all of that is used to produce electricity. Okay, so when it comes to cheap materials, and here is a picture of a cheap silicon, polycrystalline silicon. Can you see that it looks polycrystalline? It's not a uniform texture, it has grains inside it. Yes,
Yes,
so
sir.
if you look at some of the solar cells in the market, some of them look like this. Okay, so these are all polycrystalline silicon based solar cells. And what is interesting is this is like a thin film of polycrystalline material which is deposited on things like plastic or steel so that you can make solar cells which cover your entire roof or the walls or maybe the roof of your car. Can the entire thing can be a solar cell. So you can imagine, I mean, you can generate a whole lot of electricity from just that. Okay, so that is why I'll just dedicate one slide to polycrystalline materials because most conventional materials are made out of single crystal materials. But as a technology, as a future growth area, as a possible uh, career, polycrystalline materials are very very important because they are the future, so to speak. If you can make anything out of a polycrystalline material, it will invariably become much cheaper. And if it becomes cheaper, it will be more marketable and it can capture the market much better. Okay. So that is why polycrystalline materials are very, very important. They are difficult, more challenging to make devices out of them, but that is where the fun begins. That's where the research starts. So based on that, all of this discussion, let's go to the next topic, the bonds. Yeah, I call it the bonds and bands. This is the new topic for today, bonds and bands. Okay, so first is an ionic bond. Sodium chloride, for example, is an ionic bond. So I'm sure this is a high secondary material. So can somebody tell me what happens in an ionic bond? What happens? The in an electrostatic fashion. Okay, because of electrostatics. So that is the ionic bond, which is well understood. It is formed by Coulombic attraction between ions. And for example, is the sodium chloride. It has a very large cohesive energy. Not very. It has a large cohesive energy, which leads to high melting and boiling points. It has a low electrical conductivity because there are no free electrons. and it is transparent again because there are no free electrons. Okay, it's transparent to visible light, and it is soluble in polar liquids like water. Okay, so that is what happens to the ionic bond. Now, here comes the important point. Let's look at this particular picture. It talks about the total energy of a material which has an ionic bond. Now, let us ask about sodium and chlorine. So, imagine sodium, that atom, is placed here. Okay. Now, what is the potential energy of the negatively charged, or the oppositely charged rather, ion? How does it depend? How is potential energy in electrostatics? What is the formula? By R, right? 1 by R. Now, 1 by R, what kind of a, how do you do, how does it look in a graph? 1 by R? It is a what?
Rectangular
I,
hyperbola.
it's a, absolutely, it's a rectangular hyperbola. And since it is attractive, it is negative. Attractive forces are negative, right? So
Yes, sir.
this is 1 by R, minus 1 by R. Can you see this dashed line? That is minus 1 by R. Now, if I have two ions at a certain distance, they are attracted. So what will happen if they keep coming closer? Can they come very close to each other, or is there a barrier beyond which they cannot come close? At some point, what will happen? Can they occupy the same space? No, right?
No, sir.
Repulsive forces will start because of nuclear interactions. Okay. Now, nuclear interaction is not an inverse square law. It is actually something that increases very fast when the distance is small and quickly dies down as the distance increases. So this is the repulsive potential. Can you see this? So this
Yes,
is
sir.
the repulsive, this is the attractive. And as you know, energy is added, right? If there is two different sources of energy, the total energy is the sum of the energy. So the sum of the energy, can you see? It looks like this. So at shorter distances, the repulsive force dominates. As you go to higher distances, the attractive force dominates. And at very large r, it is zero. So can you see what is happening at this point? What is happening here? There's a minima, right? And if this is a minima at the distance
Yes,
r0, what is the probability of finding the atom? Where is the atom the most probable or position of the atom? At the minimum energy, because the system tends to minimize energy, as we know.
yes, sir.
So what will happen? By nature, because of these two oppositely directed forces, the atom will be at a position r0 from each other, and this is the energy that it has at this position. This is the basic reason why crystals are formed. Okay, because that is where the minimum energy is placed. Which is why, for example, salt is a crystal. You know, salt is a crystal. Anytime you look at salt, you can realize that salt grains are of the same size. They are actually cubic in nature. So this is the reason of the formation of a crystal. So what will happen if at this point you provide energy? Then it will try to oscillate. Yes. Now, do you think this slope and that slope is the same? So which way will the oscillation be more? The sharper slope or the weaker slope?
We,
Weaker slope, right? So if it keeps oscillating, it will move more towards this side, and so R0 is going to increase.
yes, sir.
So that is thermal expansion. Okay. If you heat it, material expands. That is the reason. So this is the whole story of the crystal spacing for ionic solids, and this is a fundamental reason why crystals are formed. That is why You give a whole lot of basically, if you give a system energy and time, it will finally come to its minimum energy position, and the minimum energy position it will form is a crystal. Okay, so that is that of, and then you have the
Yes, sir.
covalent bonding. You know what is covalent bonding? It's again high secondary material. Can somebody tell me what it is? It's a question of shared what? Shared what? Electrons, right? To form a
Electrons.
yes, two shared electrons. Okay, so that is covalent bonded material. Examples are carbon, silicon, and then 3,5 elements like gallium arsenide, indium, antimonide. They are formed by strong and localized bonds. See, they are directed bonds to form stable closed shell structures. Very large corrosive energy leads to higher melting and bonding points, low electrical conductivity. And of course, as you know, carbon, as in diamond, has the strongest cohesive energy. It is very hard material, and so on and so forth. Incidentally, do you know that material devices can be made out of diamond? Yes, so it has a whole lot of electronics applications. Anyway, and then the third type of solid is a metal, and this is something formed by Coulombic attraction between the lattice ions and an electron gas. Metallic bonds allow electrons to freely move. Small cohesive energy, high electrical conductivity, absorbs light. These two things are related. High electrical conductivity and absorbs light. These two things are related. Usually, insulators are transparent, conductors are not. Can you tell me why? Why are insulators transparent and metals opaque? Hmm? Anybody? Okay, we'll come to it in the next few slides. And then alloy formation due to non-directional metallic bonds. So these are the stories. Now, question: has the Abhijit covered band theory in his class?
Yes, sir.
Okay, so I can go through it quickly. It's a common structure. And so electrons surrounding a nucleus have a certain well-defined energy. And Pauli exclusion principle means we can have a maximum of two electrons at a given energy level. That's it. And so what will happen is individual atoms have electrons at similar energy levels. What happens when we start to move atoms together to form a solid? So here we go. If there are two, energy levels subdivide. And then silicon has a very, very large number of atoms. So that splits into a very small number of levels. And together, see, splitting, splitting, splitting. And finally, you form bonds, form bands rather. So the one, if there are two atoms which can see each other, it splits into two. If there are four, it splits into more. If there are n and n is very large, then these splits into something which are called bands, in which the energy are infinitesimally close to each other. If they are so close to each other, you can say that the energy is nearly continuous. And these are energy which are bands, and there are gaps between them. So I think you're all familiar with this, right?
Yes, sir.
Good. So I do not need to expand on this. So, definition of a valence band. Can somebody tell me?
Sir, where the electrons stay.
Basically, this is the definition. There is no other definition. If I go up in the band energy bands, the lower energy bands are more likely to be filled with electrons than the higher ones. Yes, energy wise. Yes.
Yes, sir.
Okay. So the last band, that is the highest energy band, that is completely filled at temperature T is equal to zero, is called the conduction. Is called the valence band. Last completely filled band is called the conduction. Is called the valence band. So, what is the conduction band? Can you define the conduction band based on the definition of the valence band? Basic, Basically, it is the band that is just higher than the valence band. That's it, right? That's it.
Yes, sir.
And so, if it is not completely filled, otherwise it would be the valence band, then what are the two options? If it is not completely filled, what are the two options? It is either completely empty or what?
Um,
Half filled? Partially filled?
partially filled.
Partially filled. So conduction band is just above, and it has either empty or partially filled. These are the two options. And the energy difference is the between the top of the valence band and the bottom of the conduction band is the band gap, which we know. Incidentally, what happens when it's partially filled and what happens when it's empty? Just a recap. At temperature T is equal to zero, if the conduction band is partially filled, what is it called? And if it is empty, what is it called? Hmm? Come on, you know this, right? If the band at temperature T is equal to zero is partially filled, it is a metal. If it is completely empty,
Yes, sir.
it is either an insulator or a semiconductor. Why do you
Semiconductor.
think if it is partially filled, it's a metal? Can somebody give me the reasoning? Why? How do you link between partially filled and your statement? What is the link? Yes. Basically, it's one more step. What you are saying is correct, but you're missing one step. In the conduction band or any band, what is the gap between energy states? Infinitesimally small. Yes, within the
Yes,
band,
sir.
right? So, if it's partially filled, the topmost energy level, which is filled, and the empty level just above that is infinitesimally close. Yes,
Yes, sir.
did you get my point? The electron that is completely filled, the last energy, the highest energy within that band, and the next empty state is infinitesimally close. So, how much energy does it take for the electron to jump to the next empty state? An infinitesimally small energy, right? A
Uh,
very small energy.
yes, sir.
So, what does it mean? A very small energy can move electrons to the next state. Yes. And if electrons are moving to the next state, gets kinetic energy, right? So,
Yes,
electrons
sir.
are moving. What is an electron that moves? What is it called? What do you call an electron that moves? No, what is an electron moving of an electron? I understand. What is an electron moving? You have a stream of electrons. What is it called? It's called a current, right? So, what does it mean? It means a very, very small potential can still drive a current. Small current, but it can. So, that is the definition of a metal. It does not require a threshold voltage before current will start flowing. Okay, did you get my point? So, the point is in a metal, even a small potential can give rise to a very small but finite current. Same story. If you shine light, what will happen? The photons will do what? If you shine light on this material which has partially empty conduction band. What will happen to the electrons? It will,
So the photons will penetrate the
photons will fall on the material, electrons will gain energy and go to the
and
next level. So what will happen to the
yes, sir.
photon? It will be absorbed. If it is absorbed, it
Yes,
cannot
sir.
pass through, right? So it is opaque. Material is not transparent. Material is opaque because the light energy is absorbed by the electrons, which can absorb it and move to the next level. Now, what happens to the possibility when the topmost state is completely empty? Then you have the gap, right? Now electrons will have to jump from the valence band to the conduction band, and that means it has to overcome this energy gap. So if I'm shining light and the photons does not have enough energy, what will happen? Hmm? If there is a band gap of say 3 electron volts and the photon energy is 2 electron volt, what will happen? They will not excite. So if it does not excite, what will happen to the photon? It will pass through.
They'll exit, but the
No, they will not excite because they cannot. If it does not excite, what will the photon do? Yes. So the material is what? Yes. So if there's a band gap, okay, if the band gap is larger than the visible photon energy, then the material is transparent. Okay. So that is the link between the fact that
yes,
most
sir.
materials which are insulators are also transparent. Most materials which are conductors are also opaque. Okay. So
Yes, sir.
that is the point. And then we go to this whole idea that you have something called the generation of electrons energy, and then there is something called recombination. What is recombination? Electrons will recombine with the holes, and then they generate energy. So this is something part of that. Figured about all this. Now this is where my we are back to my topic of this class. The topic is of course semiconductor materials. Now this comes the whole story. So these are the common materials for the 3 5 and the 2 6s, and of course the group 4s. So which one are the group 4s? Okay, so now let's name 3 5s, starting with the top. Which one is this is what? Aluminium?
Nitride,
Aluminium nitride. And how about this?
gallium nitride,
How about this?
indium
Okay, so
nitride,
these are called the nitride semiconductors. Aluminum phosphide, gallium phosphide, indium phosphide are called the phosphide semiconductors. Aluminum arsenide, gallium arsenide, indium arsenide are called the arsenides. Aluminum antimonide, gallium antimonide, indium antimonide. These are called the antimonides. So essentially, these are group of semiconductors. Each of them have their own very unique properties and very important technological uses. So these are called the nitrides. These are the phosphides. These are the arsenides. These are the antimonides. Similarly, what are these? What is this?
zinc oxide,
Okay. So this is an oxide semiconductor. And of course, there are also magnesium here, magnesium oxide and others. So these are oxide semiconductors. So zinc, and this is what? Zinc sulfide.
sulfide,
Zinc sulfide, carbon sulfide, mercury sulfide. So these are sulfides. These are selenides and these are tellurides. Okay. What I'm trying to say is all of these semiconductors are critically important for many different technological applications. You cannot leave any of them saying, ah, that's not important. All of them are important. And here comes the most important diagram of this entire story. And any of you who are going to work in semiconductors or semiconductor devices, this is the most important diagram that you have to remember. So, what is on the x axis? Can you tell me in the x axis? And what is here? And what is this? What is the link between these two? Is there a link? You remember? E is equal to hc by lambda. Okay.
HC lambda.
So,
Yes, sir.
good. Now, here comes this is 3 electron volts, which is zero point 0.4 micrometers. And so, as the energy goes down, the wavelength increases. See that? Energy goes down, wavelength increases. Now, these are the important semiconductors, not all of them, some of them. So, can you see the arsenides? Aluminum arsenide, gallium arsenide. So, this line joining these two is called an alloy semiconductor called aluminium gallium arsenide. Okay, this line represents a alloy semiconductor called aluminium gallium arsenide. Okay, just a second.
Yes,
Hold on,
sir.
just a second. Hold on. হ্যালো, হ্যাঁ আমি একটা ক্লাসের মধ্যে আছি, আমি কথা বলতে পারছি না, আমি কল ব্যাক করবো। Okay, now let us look at phosphides. Can you see the phosphides? Gallium phosphide,
Yes, sir.
indium phosphide. Now, some of these lines, can you see they are dashed lines and some of them are continuous lines? The dashed line represents alloys which are indirect band gaps. See, silicon, germanium, both are indirect. The continuous lines are those which are direct band gap semiconductors. Okay, indirect band gap, direct band gap. Now, has this been taught to you? Direct, indirect band gaps. Okay, so that I will cover in the next class. Don't worry about it. And so what I'm saying is, if this material, remember, let's go up to this class again. See that if there is a recombination, electrons and holes recombine, then light is emitted. Yes. What is the energy of the light? Is given by what?
Wavelength.
The band gap of the semiconductor, right? The energy lost is given by the band gap,
Yes, sir.
right? Energy lost is given by the band gap. So essentially, what will happen is, depending on the band gap, the light will change. Yes or no? So let's assume
Yes, sir.
we are assuming, say, gallium arsenide. So it has a band gap which has, say, here, okay, 1.44 micrometers because it has a particular energy. So what will happen that this will emit light with this wavelength, zero point 0.9, something like that, zero point 0.9, 1.44 is the energy gap, and which is zero point 0.9 micrometers, 900 nanometers. Now, aluminum arsenide has something like 400, no, something like 600 nanometers. Can you see that? This is zero point 0.5, yes? Zero point 0.5 micrometers is how much is in nanometer? 0.5 micrometers is how much in nanometers?
So 500 nanometer.
500 nanometer. And do you know what is a visible wavelength range? What is the wavelength for blue? red, and etc.? Anybody?
Sir, it's around 380 to 700.
Okay, so here you go. It's easier. I will put it right here. Can you see it now? So I've
Yes, sir.
okay. So can you see that if I make anything out of, see, here is the gallium arsenide. Can you see gallium arsenide here? This is aluminum arsenide. So this is aluminum gallium arsenide. The light coming out of it will be red. Gallium arsenide is lower than red, so it's infrared. How about here? What is this? Can you see gallium nitride here?
Gallium nitride.
And this is,
Yes, sir.
what is this?
Indium nitride.
So what is this line? Indium gallium nitride, the alloy. Okay.
Yes, sir.
And can you see blue falls here somewhere?
Yes,
So
sir.
all the blue LEDs that you see in the market, they are all made out of this particular material. Okay. So what I'm saying is all of these semiconductors are useful. This is useful for visible light emission. This is used for the red emission. Now, indium gallium arsenide. This is used for infrared emission, and this is for the communication wavelength. This is for light that passes through the optical fiber. Okay. Cadmium telluride, mercury cadmium telluride. This is used for solar cells. The most important solar cell, very efficient solar cells. Antimonide, very small energy. Okay, so can you tell me any use for anything which has a very, very small energy gap? Anybody? Given the idea that the if you look at the other reaction, we talked about this. Energy falls, and you go, electrons go from the valence band to the conduction band, and you get electron hole pairs created, which can then be detected. So, based on that, can you tell me what a narrow band gap material will be useful for? No, think. I'm talking about, of course, processor it might be, but I was talking about the fact that you have a small band gap. It it can absorb light with a very small energy, and this light can be detected. So, what is light with a small energy? How many of you still remember the Planck's theory? Do you still remember Planck's black body radiation?
Yes, sir.
Okay. So, do you still remember there was a link between energy of light and temperature?
Yes, sir.
And low temperature means longer wavelength. Yes. Higher temperature means shorter wavelength.
Yes, sir.
So, the low temperature is heat, right? And then infrared radiation. So, based on this discussion, can you tell me what a narrow bandgap material will be useful for detecting what? It is looking for very long wavelengths, small energy. It is useful for detecting heat. Okay, thermal imaging. So, have you seen thermal cameras? At least you have seen uses of thermal cameras where you can see night vision.
Yes, sir.
And why is night vision possible? Because your human body, it has low temperature, but even if it has some energy, it will emit radiation, and radiation will be in very long wavelengths because hc by lambda, smaller energy, longer wavelength. Yes. And so this has so narrow a band gap, it can detect, what can it detect? Signature from the human body. So all of these materials are used for night vision equipment. Okay. So the point of this lesson is, if you the what you're looking at in this whole picture, all of them are very, very useful semiconductors, and they all are used extensively in your daily life, not only silicon and germanium. Okay.
Yes, sir.
So that is what the end of this whole story is about. We will talk about technology coming from the next class. I will upload this entire thing today, and I will put in a little bit of homework. Okay, to be submitted
Okay,
next
sir.
class.
Okay, sir.
When is the next class?
So
Next
next class, Tuesday.
next Tuesday. Okay, so you have a week to submit your homework. Any questions regarding the class today? Good. Thank you so much. Thank you.
Okay, sir. Thank you.